In this lesson, we will move slowly from the implicit equation f of x comma y equals 0 to the first derivative and then to the second derivative. The constraint never changes. What changes is our target. Suppose we are given the implicit equation f of x comma y equals 0. This equation describes a level curve in the xy plane. Let us call the function value u, thus u equals f of x comma y. Think of x and y as positions on the input floor and u as the vertical function height. At every point on our particular implicit curve, the function value u is 0. That does not mean the function is 0 at nearby points away from the curve. Under suitable conditions, we can think locally of y as a function of x. Therefore, when we insist that the point remains on this curve, x and y are not independent. For the formulas below, assume fy is not 0 at the point, and that the required first and second partial derivatives are continuous nearby. These are the usual local conditions that let us write y as a smooth function of x. Begin at the point P with coordinates x, y on the implicit curve. Now we choose a small change in x. The movement in x is horizontal in the input plane. Because the new point must stay on the same curve, we cannot arbitrarily keep y unchanged. The curve determines the new y value, namely y of x plus delta x. Therefore delta y is defined as y of x plus delta x minus y of x. We choose delta x. The corresponding delta y is determined by the curve. Very important, we are not assuming delta y equals delta x. They are different changes in different coordinates. Their relationship is controlled by the shape of the curve. As delta x tends to 0, x plus delta x tends to x. Because the local function y of x is continuous, y of x plus delta x tends to y of x, hence delta y also tends to 0. The nearby point Q has coordinates x plus delta x, y plus delta y. Both P and Q lie on the same implicit curve. This equation records exactly why Q lies on the curve. Its y coordinate is not guessed, it is the curve value at x plus delta x. Our first target is the total change in u and x changes and y follows the curve. We are not yet differentiating the slope. At the nearby curve point, the function value may be written as u plus delta u, and it equals f evaluated at both changed coordinates. The total change delta u is the new function value minus the original function value. Divide the total function change by delta x. This measures the average change in u per unit change in x along the curve. Now let delta x tend to 0. At the same time, delta y tends to 0 because the nearby point remains on the continuous curve. This limit is the total derivative of u with respect to x along the curve. Now focus only on the numerator. We will split this one total change into two simpler coordinate changes. Add and subtract the carefully chosen intermediate value f of x plus delta x comma y. This temporary input keeps y fixed while x changes first. The original total change stays on the left. On the next line we will write it as a y effect plus an x effect. The first bracket changes y while x is temporarily fixed at x plus delta x. The second bracket changes x while y is temporarily fixed at y. Adding the brackets gives the original total change exactly. Geometrically, we imagine an x direction move and then a y direction move. The intermediate point may leave the zero level curve. It is only a device for measuring the two coordinate effects. Look only at the x part. Here y is temporarily held fixed, while x changes by delta x. As delta x tends to 0, this quotient becomes the partial derivative f sub x at x comma y. The movement in x is horizontal on the input floor, but f sub x measures the resulting vertical change in the function value u per unit x movement, with y fixed. The x-only point does not have to remain on f equals 0. That is perfectly acceptable, because a partial derivative deliberately measures one coordinate effect at a time. Now look at the y part. During this partial measurement, x is fixed at x plus delta x while y changes by delta y. After the total numerator has been divided by delta x, multiply and divide this y part by delta y. We now have the y partial quotient times the right delta y over delta x. As delta x and delta y tend to 0, the base point x plus delta x comma y approaches x comma y. Under continuity of the partial derivative, the first factor approaches f sub y at x comma y. The second factor approaches dy by dx, because delta y is the curve determined change y of x plus delta x minus y of x. Therefore the y contribution to the total rate is f sub y multiplied by dy by dx. Putting the x contribution and the y contribution together gives the total derivative of u along the curve. But along our implicit curve, u as a function of x is identically 0. Because u is the constant 0 along the curve, its total derivative with respect to x is 0. Therefore f sub x plus f sub y times dy by dx equals 0. Move f sub x to the other side, the y contribution must cancel the x contribution. Assuming f sub y is not 0, divide by f sub y. We have obtained the first derivative from the total change limit, not by jumping directly to memorized formula. Do not conclude that because f is 0 on the curve, its partial derivatives must be 0. The statement f equals 0 is restricted to the level curve. F sub x and f sub y ask what would happen under separate coordinate movements. Those temporary movements may leave the curve, so the function value can change. Only the combined total change along the constrained direction must be 0. That combined direction is the tangent direction of the implicit curve. We have finished the first job, finding the slope by studying the total change in the function value. Now our target changes. We are no longer asking how the function value u changes, we are asking how the slope itself changes as the point moves. The rate of change of dy by dx with respect to x is the second derivative d squared y by dx squared. The target has changed, but the constraint has not changed. Every actual comparison point must still lie on the same implicit curve. To measure how the slope changes, compare the slope at two nearby points P1 and P2 on the same curve. Again, delta y is not arbitrary, it is y of x plus delta x minus y of x. This requirement keeps the second point on the curve. If we change x but keep y fixed, this point will generally lie off the implicit curve. At an off-curve point, minus f sub x divided by f sub y is not being used as the slope of our original implicit curve at a corresponding nearby curve position, therefore it cannot serve as the second slope in this limit. The correct nearby point changes both coordinates, with delta y supplied by the curve. Now both slope values are comparable. From this point onward, capital P and Q abbreviate the partial derivatives f sub x and f sub y. The nearby points will be called P1 and P2, so the notation stays clear. The implicit slope is minus p over q. P and q are themselves functions of both x and y. Along the curve, y is y of x, therefore p and q become composite functions of the single variable x. Method 1 begins with the slope minus p over q, understood as a quotient of two functions changing along the curve. Differentiate both sides with respect to x. The result is the negative derivative of p over q. The quotient rule gives q times dp by dx minus p times dq by dx divided by q squared, with the original minus sign outside. Do not use the chain rule blindly. By definition, dp by dx compares p at two nearby curve points, so both coordinates change. Add and subtract p of x plus delta x comma y. This is exactly the same two coordinate split used earlier for f. After dividing by delta x, multiplying and dividing the y part by delta y, and taking the limits, we get p sub x plus p sub y times dy by dx. The same definition applies to q again. The two evaluation points stay on the curve. Add and subtract q of x plus delta x comma y. The same algebra separates the y and x coordinate effects. Taking the corresponding limits gives q sub x plus q sub y times dy by dx. For compact notation, let R equal fxx, S equal the equal mixed partials fxy and fyx, and t equal fyy. We assume the usual mixed partial equality under our smoothness conditions. Because p equals f sub x, p sub x is fxx, namely R, and p sub y is fxy, namely S. Therefore dp by dx equals R plus S times dy by dx. Because q equals f sub y, q sub x is fyx, namely S, and q sub y is fyy, namely t. Therefore dq by dx equals S plus t times dy by dx. Now use the first derivative already proved from the total change argument. Substituting minus p over q into dp by dx gives R minus ps over q. Similarly, dq by dx becomes S minus pt over q. Substitute both total derivatives into the quotient rule expression. Keep the outer minus sign and the order q dp by dx minus p dq by dx. Expanding gives qr minus ps plus p squared t over q, all over q squared with a minus sign outside. Combine minus ps and minus ps to obtain minus 2ps. Multiply the inner numerator by q to use the common denominator. Method 1 gives d squared y by dx squared equals minus the quantity q squared r minus 2pqs plus p squared t, divided by q cubed. Now derive the same result directly from the definition of derivative. P1 and P2 are nearby points on the same curve, with delta y determined by y of x plus delta x minus y of x. At P1, the slope m1 is minus p of x comma y over q of x comma y. At P2, the slope m2 is evaluated at both changed coordinates. This is essential because P2 lies on the curve. The second derivative is the limit of the change in slope divided by the change in x. Substitute m2 and m1. This long expression is simply the definition of the derivative of the slope along the curve. For readability, let P1 and Q1 denote the values of the functions p and q at the first point. Let P2 and Q2 denote their values at the second curve point. The slope difference quotient now has a compact form. Combining the fractions produces minus the numerator p2q1 minus p1q2 divided by q1q2 delta x. Now focus only on this numerator. We will rewrite it so that changes in p and q appear explicitly. Add and subtract p1 q1. The value of the numerator does not change. Factor q1 from the first pair and p1 from the second pair. Now the change in p and the change in q are visible. Move delta x into the two change terms. This displays the difference quotients for p and q along the curve. As delta x tends to 0, delta y also tends to 0. Therefore the second curve point approaches the first, and p2 approaches p while q2 approaches q. Because both p-values are evaluated at curve points, this difference quotient tends to the total derivative dp by dx along the curve. Similarly, the q difference quotient tends to the total derivative dq by dx along the curve. Look carefully, the two-point limit has produced exactly the same expression that the quotient rule produced in method 1. Use the total derivative of p already derived by the limit split and then insert dy by dx equals minus p over q. Use the corresponding total derivative of q and insert the same first derivative. Substitute these expressions into the common quotient form obtained directly from the slope limit. Simplifying gives exactly the same second derivative, minus q squared r minus 2pqs plus p squared t, divided by q cubed. Both methods measure the same quantity, how the slope changes as the point moves along the implicit curve. The quotient rule and the direct limit both visibly reach the same intermediate expression before the substitutions for dp by dx and dq by dx. Therefore both methods give the identical second derivative. The central idea is that f of x, y equals 0 ties x and y together. When we choose delta x, the change delta y is not arbitrary, it is determined by the curve. For the first derivative, we study the total change in f and split it into an x effect and a y effect. Because the actual motion stays on the level f equals 0, the total change along the curve is 0. This gives the slope of the implicit curve. Then the target changes. We stop measuring the change of the function value and begin measuring the change of the slope itself. Whether we use the quotient rule or directly compare slopes at two nearby curve points, we obtain the same second derivative. The constraint f of x, y equals 0 never changes. First, change of the function, next, change of the slope.